In the first video on continuity, we had looked at some candidate definitions for continuity, and one of these definitions was that a function is said to be continuous if and only if it satisfies the intermediate value property. However, we soon abandoned it because we realized this definition had some issues. Now that we have a formal definition of continuity, it is thus natural to ask if a function that is continuous with respect to our definitions satisfies the intermediate value property or not. And we will prove that in fact it does. And this theorem is called the intermediate value theorem. So let's state and prove the intermediate value theorem. Let I be an interval and f be a function from I to R that is continuous on I. If a comma b belong to I, and if k belonging to R satisfies f of a is less than k is less than f of b, then there exists a point C in I such that f of c is equal to k. This is the intermediate value property. Let's see how we can prove it. We had seen that the intermediate value property is a consequence of the fact that there are no gaps on the real line. For example, we had seen that if you have a function from the rational numbers to R, then it need not satisfy intermediate value property. We had seen that as an example when we discussed intermediate value property in the first video on continuity. And what was really the difference between the set of rational numbers and set of real numbers? How did we go from the set of rational numbers to the set of real numbers? The only extra added ingredient was the completeness property. That means every bounded set has a least upper bound. So somehow we should guess that the proof of this theorem will be using that completeness property. So that's the first case. So we already know that we have to use the LUB axiom to prove this theorem. How will we use this? So what do we want to show? We want to show that the function takes the value k at some point. So we look at all the values, all x's. Okay, so I define a set S such that S is the set of all x such that f of x is less than k. Here x is an element of AB. So we are looking at all elements in AB such that f of x is less than k. Clearly this set S is bounded because it's a subset of AB and AB is bounded. Hence it has a supremum. So let us call C to be equal to supremum of this set S. From the way I have named the supremum of S, it is quite clear that I am going to claim that f of C is equal to k. And in some sense, this is intuitively clear why f of c has to be k. If you take a number greater than c, then clearly f of that number has to be greater than k. And if you take any number, say c dash less than c, then there exists some number between c and c dash such that f of that number will be less than k. So you have numbers that are arbitrarily close to c and less than c such that f of those numbers will all be less than k, and every number that is greater than c has the property that f of that number is greater than k. So in some sense it's sandwiched between numbers at which it takes the value less than k and greater than k. So at C it should take the value f of c equal to k. At least that's the kind of intuition that we have. Now let us try to prove this rigorously. So because f is continuous at C, for every epsilon greater than 0, there exists a delta that depends on epsilon which is also greater than 0, such that mod of x minus c is less than delta implies that mod of f of x minus f of c is less than epsilon. So I can write this mod of f of x minus mod of f of x minus f of c is less than epsilon as f of x minus epsilon is less than f of c is less than f of x plus epsilon. Now the next thing you notice is that c minus delta is not an upper bound for s. Why? Because c is the supremum. So any number less than c cannot be an upper bound. Hence there exists some number a1 that belongs to s intersection c minus delta to c. Thus from the inequality for continuity we get that f of c is less than f of a1 plus epsilon. Why? Because for any x which belongs to c minus delta to c plus delta, this inequality is satisfied. And in particular, a1 belongs to this interval and hence it is satisfied. On the other hand, if it belongs to a1 belongs to s implies that f of a1 is less than k. Okay, and because f of a1 is less than k, we get that f of a1 plus epsilon is less than k plus epsilon. Notice here it is actually there exists a1 in S intersection c minus delta to c. I had said it but I had not written it. On the other hand, if you take any a2 belonging to c comma c plus delta, the interval c comma c plus delta, this implies that a2 does not belong to S. If a2 does not belong to S, what does this mean? This means that f of a2 is greater than or equal to k. Okay, and we know from the inequality for continuity that f of c is greater than f of a2 minus epsilon, which implies that f of c is greater than k minus epsilon. So together what do we have? So let's call this equation 1 and let's call this equation 2. We get 1 plus 2 implies that k minus epsilon is less than f of c is less than k plus epsilon. And notice that this holds true for every epsilon, which implies that f of c has to be k. That is the only possibility. And hence we have completed the proof. Another property of continuous functions that we saw was that if f is continuous at a point c, then it is actually bounded in the neighborhood of c. More precisely, there exists some delta such that f is bounded in c minus delta to c plus delta. Okay, and what exactly do we mean by f is bounded? There exists some capital M such that mod of f of x is less than or equal to m. So this naturally leads to a more general question. What is this question? So if a function f from a to r is continuous everywhere, then is f bounded? Okay, we kind of expect some such result because if a function is continuous at C, then you have some neighborhood in which it is bounded. So if it's continuous at every point, maybe you can get a global bound. That's what you would expect, right? Maybe you should pause the video now for a few minutes and then think what the answer to this question should be. I hope you have come up with an answer to this question. The correct answer is that it is not necessary that f is bounded. Let me give one example illustrating this fact. So look at the function f from 0, 1 to r given by f of x is equal to 1 by x. Clearly f is continuous at all points. But f is not bounded. How do we see this function is not bounded? Look at the sequence xn is equal to 1 by n. Then f of xn is equal to 1 divided by 1 by n, which is equal to n that converges to infinity. And each of these 1 by n belongs to 0, 1, the interval 0, 1. So you have points whose values can be as large as you want. And because of this, we know that this function f is not bounded. Okay, why is this happening? Let's try to see why this is happening using a picture. So we have the graph of the function looks something like this. As the x gets closer and closer to 0, the value gets bigger and bigger. So what is happening is at each point we have a neighborhood on which the function is bounded. Namely, whatever is the distance of the point to 0 is the size of the neighborhood that you can take. So as it gets closer and closer to 0, it gets the neighborhood in which the function is bounded becomes smaller and smaller. And that is kind of the reason why there is a problem. Another way to look at it is, if you look at the sequence xn, this xn is converging to 0, which does not belong to the domain of 0, 1. That's another way of looking at this. So in some sense, the problem is that 0, 1 as a set has this property that there exist sequences in 0, 1 that converge to a point not in 0, 1. Okay, and this is kind of the problem. So if we can avoid this issue, then we should expect that the function will be bounded. So what do we see here? If we want continuous functions to be bounded on a domain, then the domain should be nice in whatever sense. And we will give one condition on the domain which will ensure that continuous functions are bounded. This is that the domain is actually a closed interval. Let's prove this theorem next. Theorem: let I is equal to AB, a closed interval, and f from I to R be a continuous functions. Then f is bounded on I. Proof. We will prove this theorem using contradiction. So the proof is by contradiction. Assume f is not bounded. What does this mean? This means that whatever value you take, there exists at least one x for which f of x is greater than that value. In particular, we can take every integer and you can find an x such that f of x is greater than that integer. Okay? That means, what does this mean? This implies that for every n in natural numbers, I can find an x, there exists an x that depends on n such that, let's actually call this x of n as xn, just to think of it as a sequence, okay, such that f of xn, where xn is nothing but x of n, is greater than n. So xn is a sequence in I, but I is bounded. So xn is a bounded sequence. We know that if a bounded sequence has a convergent subsequence. Okay, so xn has a convergent subsequence xnk as xn is bounded. Let us further say that xnk converges to x. But notice that a is less than or equal to xnk is less than or equal to b. So from limit theorems, we know that this implies that a is less than or equal to x is less than or equal to b, which implies that x belongs to I. Okay, so what can we do? Because x belongs to I, we know that f of x and k converges to f of x. Why? Because f is continuous. But if f of x and k converges, that means that f of x and k has to be bounded. This implies that the sequence f of x and k is bounded. But notice that f of x and k was nothing but nk, which is not bounded. So this is actually a contradiction. Hence, the beginning assumption that f is not bounded has to be wrong, thus proving our theorem. So we have seen that if I is equal to AB, the closed interval, and f from AB to R is continuous, then f is bounded. More precisely, the set S is equal to the set of all f of x such that x belongs to I is bounded. Because of this, M is equal to infimum of S and capital M is equal to supremum of S exists. Why? By completeness property. So completeness property tells that these two will exist. Okay. Now the question is that is there some value for which these are attained? Does there exist? Okay. Question: does there exist C0 and C1 in I such that f of C0 is equal to small m and f of C1 is equal to capital M? And the answer is that, and the answer happens to be yes. Let's try to prove this. We will prove that there exists a C0 such that f of C0 equal to m. The proof that f of C1, there exists a C1 such that f of C1 equal to capital M is similar, and I leave that as a homework. So how do we show that there exists a C0 such that f of C0 is equal to m? So notice that if you take small m plus 1 by n, that is not a lower bound. Which implies there exists some x that depends on n such that f of xn is less than m plus 1 by n. Okay. Now this, we can do this for every n. So xn belongs to I for all n, which implies that xn is bounded. The sequence xn is bounded, which implies that there exists a convergent subsequence x and k. Let's say it converges to x. Notice further that m is less than or equal to f of x n k is strictly less than m plus 1 by n. Further notice that f of x and k converges to f of x, as x and k converges to x and f is continuous. So if you use the limit theorem, what this says is that m is less than or equal to f of x is less than or equal to m, which implies that f of x is equal to m. So this was the C naught that we required. Similarly, we can show that there exists a point at which the value of f is equal to capital M. And I leave the proof of that part as a homework. So what did we see so far? What we were interested in were functions f from I to R, where I was the closed interval a comma b. We saw that if m is equal to infimum of f of x such that x belongs to I, and capital M is equal to supremum of f of x such that x belongs to I, then there exists C naught, C naught comma C1 such that f of C naught is equal to small m and f of C1 is equal to capital M. Further notice that the image f of I is certainly contained inside the closed interval small m comma capital M. So f of I is contained inside the interval small m comma capital M. And moreover, f of C naught is equal to small m and f of C1 is equal to capital M. So what do? We look at the restriction of the function f to the interval C naught comma C1 and apply the intermediate value theorem. This says that for every k in the interval small m to capital M, there exists an x in C naught to C1 such that f of x is equal to k. That means every element, every value in the interval small m to capital M is attained by some point. So this means that f of I is actually equal to the interval small m comma capital M. Thus we have proved that the image of a closed interval under a continuous map or function, continuous function. I sometimes use map and function as interchanged. Map just means function. Is a closed interval.